In section 3.3, we're going to look at zeros of polynomial functions, the factor theorem, rational zeros theorem, number of zeros, conjugate zeros theorem, finding zeros of a polynomial function, and Descartes' rule of signs. The factor theorem states, for any polynomial function f of x, then x minus k is a factor of the polynomial if and only if f of k equals 0. So the factor theorem is very similar to the remainder theorem. If f of k is equal to 0, then x minus k is a factor or a divisor of the polynomial. Example 1. Determine whether x minus 1 is a factor of each polynomial. Part A. F of x is equal to 2x to the fourth plus 3x squared minus 5x plus 7. By the factor theorem, x minus 1 is a factor if f of 1 equals 0. So we're going to use synthetic division and the remainder theorem to decide. So for our divisor, we're going to put 1 because we're using the opposite of negative 1. So we'll put 1 as our divisor. And inside we'll put our coefficients. We have a coefficient of 2, and that's why there's a 2 here. The 0 is necessary because it is a placeholder. The 0 is necessary because it's a placeholder. We're missing a power of 3, so we'll use 0 as a placeholder. 3 is our coefficient for x squared. Negative 5 is the coefficient for x, and 7 is our constant term. So let's use synthetic division. We'll drop down the 2. And then we'll multiply. 1 times 2 is 2. 0 plus 2 is 2. And then we'll multiply. 1 times 2 is 2. 3 plus 2 is 5. 1 times 5 is 5. And negative 5 plus 5 is 0. 1 times 0 is 0. And then we'll add 7 plus 0, we get 7. The remainder is 7. The remainder is 7. That implies that f of 1 gives us 7. That means, by the factor theorem, x minus 1 is not a factor. It has to be equal to 0 for this to be a factor. The remainder has to be equal to 0 for this to be a factor. Part B, we want to determine whether x minus 1 is a factor of, this time f of x equals 3x to the fifth minus 2x to the fourth plus x cubed minus 8x squared plus 5x plus 1. We'll use synthetic division again. Since x minus 1 is a factor, we'll use 1 as our divisor. Since we are interested in determining whether fx minus 1 is a factor, we'll use a positive 1 as our divisor. And inside we have the coefficients 3, negative 2, 1, negative 8, 5, and 1. And we'll use synthetic division. First, drop down the 3. Multiply 1 times 3, we get a 3. Negative 2 plus 3 is 1. Then we'll multiply 1 times 1, and that is 1. 1 plus 1 gives us 2. 1 times 2 gives us 2. Negative 8 plus 2 is equal to negative 6. 1 times negative 6 is negative 6. 5 plus negative 6 is equal to negative 1. 1 times negative 1 is negative 1. And 1 minus 1 gives us 0. So the remainder is 0. That implies, according to the remainder theorem, f of 1 is equal to 0. Then x minus 1 is a factor. Example 2. Factor f of x equals 6x cubed plus 19x squared plus 2x minus 3 into linear factors if negative 3 is a 0 of f. Since negative 3 is a 0 of f of x, we have that x minus a negative 3 or x plus 3 is a factor. So we'll use synthetic division with negative 3 as our divisor, and we'll put our coefficients 6, 19, 2, and negative 3 inside our symbol. And we'll use synthetic division. We'll bring down the 6. Negative 3 times 6 is negative 18. 19 minus 18 is positive 1. Negative 3 times 1 is negative 3. 2 minus 3 gives us negative 1. And negative 3 times negative 1 is positive 3. And we have the remainder is 0. Since the remainder is 0, then we also have that this part of it is a factor of our polynomial function. This quotient here is equivalent to 1 degree less than the original polynomial. We had a degree of 3, so we're going to start with a power of 2. So this is equivalent to 6x squared plus x minus 1. So 6x squared plus x minus 1 is also a factor of f of x. Then we have f of x can be written in the form x plus 3 times 6x squared plus x minus 1. I can use the AC method to factor 6x squared plus x minus 1. Negative 6 is going to go on top, positive 1 is going to go on the bottom. The two numbers that multiply to get 6 are 3 and 2, but we need this to be a negative, so we'll attach the negative to the 2 because it has to add up to a 1. Using the AC method, we'll divide this by 6x, so I have 1 over 2x when I reduce it to lowest terms, and this is negative 1 over 3x. We'll use the bottoms up technique to factor the right side. And this gives us f of x equals x plus 3 times 2x plus 1 times 3x minus 1. These factors are all linear. The rational zeros theorem states if p over q is a rational number written in lowest terms, and if p over q is a 0 of f and a polynomial function with integer coefficients, it has to have integer coefficients, then p is a factor of the constant term and q is a factor of the leading coefficient. Let's try out the rational zeros theorem. Consider the polynomial function f of x equals 6x to the fourth plus 7x cubed minus 12x squared minus 3x plus 2. According to the rational zeros theorem, we're going to use the 2 as our p, and the leading coefficient is going to be our q. First, I am going to list all of the factors of 2. The factors of 2 are numbers that divide into 2. So we have a 1 and a 2 are the only numbers to divide into 2. Then we'll list all of the factors of 6. The factors of 6 are 1, 2, 3, and 6. 1, 2, 3, and 6 all divide into 6. So according to the rationals root theorem, we have that our possible P over Q's can be any of these numbers over any of these numbers. The factors of 2 are going to represent our possible numerators, and the factors of 6 are going to represent our possible denominators for our rational zeros. So we'll take 1 and we'll divide it by each of the denominators. So I have 1 over 1, 1 over 2, 1 over 3, 1 over 6. And then I'll take 2 and I'll divide it by each of our q's. 2 over 1, 2 over 2, 2 over 3, and 2 over 6. Now we'll have to simplify. P over Q can be equal to 1 over 1 is just 1. And we have a 1/2, a 1/3, a 1/6. 2 over 1 just simplifies to 2. 2 over 2 is the same as 1, so we are not going to repeat ourselves. We'll just leave it as a 1. 2/3 we don't have, so we'll put 2/3. And the last one is 2 over 6, so we'll just have these as our possible rational roots. But remember, P can be positive or negative, and Q can be positive or negative. So we have to make sure we put a plus or minus in front of each of these factors because they could possibly be positive or negative. So don't forget when you're using the rational root theorem to put a plus or minus in front of each possible rational root. Consider the polynomial function f of x equals 6x to the fourth plus 7x cubed minus 12x squared minus 3x plus 2. Find all of the rational zeros and factor f of x into linear factors. Use the remainder theorem to show that 1 is a zero. Now we're using all of our possible rational roots from earlier, and we usually start with the easiest one. We start with 1. But then again, this is a trial and error method, so 1 might not work. If 1 doesn't work, we use the next number, -1. If 1 doesn't work, we'll use -1. If -1 doesn't work, we'll use 1/2. And then if that doesn't work, we'll use -1/2 and so on until we have done all of the rational roots. It's always a good idea to do the nice numbers like 1 and whole numbers like 2. This is a trial and error, so you don't have to go in order. Let's use 1 with synthetic division. We have coefficients 6, 7, -12, -3, and 2 into our dividend, and we'll now use synthetic division. Bring down the 6. 1 times 6 gives us 6. 7 plus 6 is 13. 1 times 13 is 13. -12 plus 13 is 1. 1 times 1 is 1. And -3 plus 1 is -2. 1 times -2 is -2. And we have this adds up to 0. So our remainder is 0. Our remainder is 0. That means f of x can be written as x minus 1, since f of 1 produces a 0, we know that x minus 1 is a factor. And since that is a factor, this implies that this is also a factor. Since the remainder is 0, this is also a factor. and we're going to use 1 degree less than the original polynomial. So this is a cubic term. So it's 6x cubed plus 13x squared plus x minus 2. Since we have factored out x minus 1, our function is simpler to factor. Now we just need to factor 6x cubed plus 13x squared plus x minus 2. Now we're going to use synthetic division with 6x cubed plus 13x squared plus x minus 2, which is a much simpler function now than what we started off with. We will use trial and error, and we will again pick from one of these P over Q's. Now there looks like a lot of possibilities, and there is. But I would recommend you start with the easiest numbers like 2 and 1. So we could test those as our rational zeros and see if they work. A good tip is to use a calculator and plug in these values into the original function f of x. If you plug these values into the original function f of x and you get a 0 from it using a calculator, I would recommend using a calculator, that will tell you that it must be a root. So that's a good tip. Use a calculator, plug in a number, and you'll realize if it gives you a 0, it must be a root. Now I have done that, and I know that negative 2, when you plug it into the function, gives us a 0. So f of negative 2, if you were to plug it in a calculator, you would get a 0. Now we are going to use the quotient polynomial and synthetic division to find that negative 2 is a 0. Now how do I know negative 2 is a 0? I plugged in negative 2 into the original function f of x with a calculator, and I got a 0. So we really don't have to struggle with trial and error. We can just plug it in with the calculator, and we know if it gives us a 0, the remainder should be 0 when we do synthetic division. Now we'll use synthetic division on our quotient, 6x cubed plus 13x squared plus x minus 2. I do not want to use it on the original factor because we already factored it part way by taking out the x minus 1, and we'll use it on the remaining quotient because it's simpler. So let's use synthetic division with negative 2. We'll drop down to 6. Negative 2 times 6 is negative 12. 13 plus negative 12 gives us a 1. Negative 2 times 1 is negative 2. 1 plus negative 2 gives us negative 1. So we have this is equivalent to 0. And that is our remainder. This means that x plus 2 is a factor. And from earlier we had x minus 1 is a factor. And since x plus 2 is also a factor, we can write f of x as x minus 1 times x plus 2. And now we can translate this into a polynomial factor. Since it's 1 degree less than 6x cubed, we have this is equivalent to 6x squared plus x minus 1. So now we're almost done factoring f of x. It looks like f of x can be factored further. 6x squared plus x minus 1 could be factored further. So here we have f of x equals x minus 1. And we factored out x plus 2, leaving us 6x squared plus x minus 1. And again, we'll use the AAC method. We have negative 6 on top, 1 on the bottom. The two numbers are 3 and 2. So this has to be a negative 2. And we can use the AC method Let's divide both of these by 6x. Simplify. I have 1 over 2x here. And this becomes negative 1 over 3x. Using the bottoms up technique, this factors as f of x equals x minus 1 times x plus 2. And we're going to bring the bottom up, so this becomes 3x minus 1. Bring the bottom up, this becomes 2x plus 1. So this is our function now factored into linear terms. So if we want to find the rational zeros and factor f of x into linear equations, we can start by setting each of our factors 3x minus 1 equal to 0, 2x plus 1 equal to 0, and that yields the zeros 1/3 and negative 1/2. So in summary, the rational zeros are 1, negative 2, 1/3, and negative 1/2. The linear factorization of f of x. The linear factorization of f of x is f of x equals 6x to the 4th plus 7x cubed minus 12x squared minus 3x plus 2 becomes our x minus 1 times x plus 2 times 3x minus 1 times 2x plus 1. And if you want to check your work, you can FOIL this out and you should get the original polynomial. I want you to note that in example 3, once we obtained the quadratic factor 6x squared plus x minus 1, we were able to complete the work by factoring. However, it's not always the case, so had it not been easily factorable, we could have used the quadratic formula to find the other two zeros and factors.